In this video, we cover nonlinear regressions. One approach to do nonlinear regressions is if you have a relationship that is, for example, logarithmic, what you can do is just transform your dependent variables and then fit a linear regression. So that's one approach that people have been using for a long time to go about it. But it's not ideal, and I will cover why that is. So as an alternative, you can fit nonlinear functions. R is actually not particularly good at this, but it still works. And we'll cover what you have to watch out for. So one of the problems that you have to deal with is overfitting, and what can help you there is the Aka-Ike information criterion. So a nonlinear regression, that is a situation where your data does not fit a straight line. So here we have a pronounced curve. So this could be, for example, a logarithmic relationship. And one way people have dealt with that problem is to simply transform your data. So you can transform your y-axis with a log2 transformation, for example. So if I do that here, my y value doubles at every tick mark, or it could be also a log10 transformation that goes from 1 to 10 to 100 to 1,000 and so on. And what that does is the long tail of the distributions toward the higher value gets reined in, because the larger values get compressed more on this axis than the small values, right? So from here to here, I compress by 128. From here to here, I just compress by 4. And so that can make my relationships nice and linear. Then I can just fit a normal linear regression function through my data, and everything should be okay. But it's not an ideal solution. If you back transform this and plot your line on the back transformed graph, it does not actually go through the center of this. It's slightly biased. And the reason for that is that since the bigger values get compressed more, your residuals that are above your line don't have as much pulling power to put that line through the center. So this bias here is exaggerated in my graph, but the function fit would be slightly biased toward lower values. So in order to avoid this, what you do is you can directly fit a nonlinear function. And that is usually done with a trial and error approach. So you can also apply a trial and error curve fitting approach to a linear model. And the way this works is that you state your equation with the two parameters that need to be estimated here, a and b in this particular case. And you just give it a guess. You look at your scatter and you say, well, maybe a could be 5 and b could be something like 1. And so what I can do then, or what the computer can do, is calculate the residual error for each of the points here. So this I indicated with this purple. And what I find, if my guess is not particularly good, is that my residuals would be quite large, right? So I get quite large residual errors here because my line just does not go through that point cloud. And then what the computer does is it varies that value for A and for B. So it starts with A, perhaps, and tries a slightly smaller value and recalculates the residual error. So does the residual error get better? If it does, it keeps going. So it will try A equals 3 until it gets worse again, right? So, and then it goes back and maybe half a step and tries 2.5 or something like that, until you arrive at a point where this does not improve anymore. And then it will tackle the next parameter and do the same thing for the slope. So it will tilt the axis and see if the residual error gets better or worse. So I made these two loops here for the two parameters, but there will be further loops. Once you optimize your second parameter, you might want to try to optimize your first parameter for the new value of b again. So it's an iterative process, and the computer can do this rather quickly and come up with a really nice function fit that minimizes your residual errors. For 2 parameters, it's pretty easy to do. 3 parameters, that can become a little bit more tricky. And 4 parameters is really difficult, at least for R. 4 parameters is something that R invariably fails to do. Even 3 parameters can be problematic. And because it's a guessing game, you can help with the curve fitting function by providing good starting parameters. So if you make a plot of your point cloud, you can guess what A and B is, right? So you can look at it and see, okay, maybe this A parameter should actually be around 0. and the b parameter, you would have to count this out. So if you go 1 unit to the right, how many units would you go up? So you can enter this as start parameters, and if they are reasonably accurate, then R will be much better in solving 3 or 4 parameter curve fitting problems. So in order to get a bit of an overview what options you have for nonlinear functions, and also to help provide start parameters for the curve fitting, we'll go over some common nonlinear functions that you can use. So parabolic functions are actually quite useful in ecology. It's actually the reverse that comes handy, where you perhaps model some sort of habitat optimum. So perhaps the x-axis here is an environmental factor, like a climate factor from low temperatures to high temperatures, and your y-axis is some dependent variable like growth of a tree. And there's always temperature condition that's too cold or too hot for the tree to grow, and somewhere in the intermediate range you have a maximum. So this can often be estimated quite well with a parabolic function. And it's not particularly complicated, so you have 3 parameters, a, b, and c. A is the top or the bottom of the parabola. C is the x value, where the maximum or the minimum occurs. And b is a scaling parameter that determines the width of the parabola, and positive and negative values flip it. You can just put in a +1 or a -1 to reflect whether you want to model a maximum or minimum, and R will figure out the rest. Logarithmic and exponential functions are also very common. They have very similar shapes, with one major difference, that the exponential function, they approach an asymptote, so they get nearer and nearer to that value, but they never hit it. And logarithmic functions, you have to watch it. If you get negative values here, they behave in weird ways on the other side. So this is only good for positive x values. You can use either one of them, so they both fit any sort of biological growth data typically quite well. The formulas are similar here, again with 3 parameters. In this case, if you have trouble fitting that function, so if R cannot find parameters for a, b, and c at the same time, you can also set a to a fixed value. So this can be 0 if you start from 0. So that's often the case with growth curves. At time 0, you start with 0, and then you can actually drop this parameter entirely from the equation. Or if you start with a small fixed value that you can just estimate based on your data, then you can also temporarily set this to that particular value. That is the intercept with your y-axis. So you can fix that and just give it a number that you infer from your point cloud where it ends here, and then R only has to estimate 2 parameters in either case. So 2 parameter fit is usually not a problem. Hyperbolic functions. So these are also possible, that you approach 2 asymptotes. And again, if that's too many parameters, you can fix a and b or set them to 0. Gaussian and sigmoidal functions are important. This one can be used just like a parabolic function. So if you have a growth or frequency response variable as a function of an environmental factor with some sort of environmental optimum, that's a widely used equation. The difference is that the extreme environments, you may still have a tail of observations. So if you see that in your data, then use a Gauss rather than a parabolic function. Sigmoidal function is related. These actually have things in common here in the equation. This is also widely applicable. To give a forestry example, the biomass of a forest stand may follow a curve like this. So they tend to start out slow because seedlings don't produce a lot of wood. Then they have some sort of rapid growth phase, and then it levels off as the trees mature and they don't grow into the sky. So sigmoidal functions are certainly very common in biology and environmental science. And the last function I'm going to mention here is a Michaelis-Menten equation. That's a beautiful function, so simple, right? Ax divided by b plus x. And it's a half-life function, so if your b parameter is negative, that half-life function would describe, for example, radioactive decay. but also some sort of enzymatic reactions. We have a substrate that gets used up in some sort of consumption activity. Or the reversal is a substrate gets converted into something else by an enzyme, for example. If you have lots of substrate and very little product, so the initial reaction is quite quick, but it tapers off and reaches a maximum when all the substrate is used up and converted into the product in the end. So you have a couple of options now in terms of choosing nonlinear equations. And which one should you use, right? So the answer number one, the most important one, is you should pick an equation that makes conceptual sense. So if you're fitting a logarithmic function to tree growth, even though that may fit your data initially quite well, it doesn't really make sense because trees will not grow into the sky, right? So the growth will taper off eventually. So you should pick a function that is actually conceptually sound. So the equation should reflect the biological mechanism. The second criteria is that it should fit your point cloud well. So one of the most important things, once you have an equation, check it against your point cloud. So R is not infallible. Sometimes the equations that pop out really don't fit. That is an important check that it visually fits. And it should also explain the most variance. If you have multiple equations to choose from, then use the one that fits best and explains the most variance. But that needs to be balanced against the simplicity of the equation. And I can show you this here with an obvious example of overfitting. So let's say you have these 4 points and you want to fit an equation here and establish a relationship between the x and y variables. You can always find a polynomial function that goes through every single point. So this is an extension of the parabolic function. So if you add x to the power 3, x to the power 4, and so on, you will always find a function that fits through every single point. But that is actually overfitted and it does not reflect reality. So in reality, your data is noisy and some of these up and downs are simply error. And if you were to estimate an intermediate point here, it would not fall exactly onto this line. So the right way to go about it in this case would be just to fit a linear equation. And normally you obviously have more than just 4 points, so this is just a conceptual example here. In a more complicated situation, there's actually a very useful criterion to determine a function that best balances the model complexity with the variance that the function can explain. That's called the Aka-Ike information criterion and is abbreviated as AIC. It's a calculation that arrives at a model complexity value that's driven by the number of parameters that you put in, minus the likelihood of the model. So this is equivalent to the model fit or to the variance explained. So the bigger this value is, the worse is your model. So if you have a very complex model, that number will be big. And if your model fit is really poor, this number will be very small. So a lower AIC is a better model. So you want one that is simple and that explains a lot of the variance. And the AIC value is not like an R square that has a meaning by itself. Out of context, the AIC value does not mean anything. It can have any kind of value. It is only interpretable in comparing 2 or more functions using exactly the same data. So the one with the lower AIC would be the better model. But if they have similar AICs and the model fit is also visually similar, then you can also, again, use that first criteria here as the most important one. So it should make conceptually sense. You shouldn't blindly go with that AIC value there. Like any other statistic, it's driven by random noise. This one here remains your most important decision criteria, what function to use. And just because the curve fitting can be a bit of a frustrating exercise if you start out with this, I just want to walk you through an example here that's from the lab. So we are going to import some data and plot it. So we have a sigmoidal function here that we want to fit. So our data follows the shape of a sigmoidal function. I already entered the equation that we discussed before with all the different parameters. And if I run it, I'm just getting an error. So that's not going to work. There are just too many parameters and R can't find a solution. So the first thing that I would do is delete the d here, because the d was the intercept at the bottom, or the asymptote at the bottom, and I see it's a 0, so I can set it to 0 or simply get rid of it and see if that works then. And again, you get an error message here, a warning message that doesn't work. So without starting value, it's not going to be happy, but we can figure out what they are, right? So A is the asymptote at the top, so I guess that's about 85, so that's what I added here. Then C is the inflection point here in the middle, where it goes from a left curve to a right curve. So that's about 4, that's what I put here. And B, I have no idea what it is, so if that's the slope. And you can try a 1, and let's see if that works. That doesn't work. We can try a -1. That doesn't work, so it's still unhappy. We can try a 0. And there we go. So it can work with a 0. So the true value is 0.2. I would also, if you don't have luck with a 0, try plus 0.5, minus 0.5. So if you don't know what the parameter is, those are your best guesses. And also the other ones here, R can find out if you're off by a little bit. Let's say we estimated 75 here. Can still solve this by trial and error. But let's say we try 5 here, which is really totally off. Then again, you get an error, and it can't find a solution to this. So getting the appropriate starting values is important. And now that we have those values here, we can copy them into an equation to add a curve. So 85.9, 0.2, and 4.0. So let's see how that looks. And that's also always a nice visual confirmation. You want to make sure that the curve actually fits your point. So that looks good. And we can also try just a linear model, how that would look. So a intercept of minus 6.9 and slope of 12. And that doesn't fit my data too well. It's a simple model, but then my AIC will tell me that the sigmoidal function is actually a much better one. So if I wrap that, either the linear model or the NLS function, into an AIC command, I'll get 28 for the sigmoidal function. And despite the linear model being simpler, the fit is so bad that it gets a much bigger value. So you go with a smaller value. That's the function you should use. So with that, you can proceed to Lab 9 to try all these things out for linear and nonlinear regression.